Hello, today I'm going to talk about reinforcement learning-based flow control. So our example is airfoil flow control. My name is Qiong from New Mexico State University. So reinforcement learning flow control, reinforcement learning techniques has been widely applied in robotics, game, and other type of the technologies. Also, there's a few examples about using the reinforcement learning to design the flow control for the circular cylinder, as I show here. The good thing about reinforcement learning, to design the feedback loop flow control, for example, in our cases, and reinforced feedback loop flow control, it has an advantage compared to the open loop flow control, which doesn't have the feedback systems. So the feedback loop flow control can adjust its actuator depending on the feedback from the flow field. So in that cases, it can handle some variations or challenging in the flow field, which cannot be handled by the open loop flow control. On the other hand, the feedback loop flow control usually has a less energy cost compared to the open loop. So it sounds really attractive. However, design a feedback loop flow control is really a challenge, particular for the high-order nonlinear flows. So as we mentioned, recently development of reinforcement learning combined with the flow control shows a great potential of design the feedback loop flow control. Examples like a low Reynolds number flow over the circular cylinder and try to reduce the drag or stabilize the oscillations. Their successful cases has been implemented to using the reinforcement learning flow control. So in such a context, we implement reinforcement learning-based flow control for natural laminar flow airfoil to enhance its aerodynamic performance. Here we focus on the increased lift. So we evaluate several important parameters to figure out how to effectively design the reinforcement learning-based flow control. So without further ado, I will give a brief introduction about reinforcement learning. In the case of reinforcement learning, the agent or the deep reinforcement learning agent interacts with the environment. As you see here, interact with the environment. So in our cases, it's a CFD environment. So the agent interacts with the CFD environment through three channels. First is observed state. This is what we set up, and it's a variable we want the agent to quickly see in order to make a decision. The second is a reward. The reward is provided to agent in order to training the agent to get optimal policy. And the third is action. The deep reinforcement learning agent will make a decision on the other two channels, like what we provide for the reward and what we provide for the observed state. It will make the action and to training the agent get optimal policy. And then the idea is trying to control the environment towards a maximum cumulative reward state. So in that it's a feedback. It's also a feedback how it interacts with the CFD environment. So in our cases, the environment is a CFD simulation. We set up a flow over natural laminar flow airfoil at Reynolds number 5000, depending on the core length and angle attack of 5. So we use a CFD solver, it's NAC 5000. We validated the simulation, it's mesh independent. So here's the action. So we choose two actuators. First is around here in the upstream. Another is right at the beginning of the separation bubbles. And the action we have is a blowing, suction, blowing, and suction. It's three different. We're going to test these three different actuators. So we test the two different locations and the three different actuators to see what's the difference in the learned controlled policy. Then the reinforcement learning, we explained the deep reinforcement learning agent. It's a two sides of the neural network. So the first one is actuator, then another one is called the critic. So these both neural networks share the same architecture. In our cases, it has two hidden layers. Each of them contains 512 neurons in each layers, and they're going to be an input layer for the observed state and output layer for the action distribution and the discounted reward. As we mentioned before, we want to increase the lift, so we design a reward function by maximize the lift with a penalty of increase the drag. So we don't want to, if it increase the lift but at the same time increase the draft, we don't want that happens. So we have the penalty implement in the reward function. So this A coefficient is actually coefficient. So we choose from the small value to the large value and to see is it going to affect the control performance. Also, as we mentioned, there's an important thing about this is a reward function, observed state. So we have full set of award state. We have the award state, observed state at the flow field, which will provide two components, velocity components, to the reinforcement learning. Or we have the observed state on the airfoil surface, so it will provide the pressure to the reinforcement learning agent. That's how we design our reinforcement learning based flow control. Then here we show is a control results. First, we compare this different reward function. Specifically, we verify this A value from the small value, like 0.2 to 10, to see is it going to change the control performance. So we see actually it doesn't really change the control performance that much. If we can see from these results, it has a slightly a drag increase, but seems like doesn't have the strong effect in our cases. So the control effect of different definitions of reward function is actually pretty minor, negligible. So the next we talk about the control actuator. So we have three actuator: blowing, suction, and blowing and suction. So in these cases, we compare with the blow suction, blowing, pure suction. So we see actually so first I see this is a lift and this is a drag. When we have the suction and the blowing, the suction actually works better than the pure blowing, even from this drag time history, you can see here has a low drag is a section, then the next is a blowing section, and we have the hair drag at pure blowing. So here we compare two actuators at different locations, and we see it does have an effect on the training processing. If we evaluate what's the effect, and we can see for this training section, when we have the actuator located upstream, and we get a hair lift increase, also have the slight increase on the drag side. So when we move to the further downstream, and we have a less lift increase, also the drag reduces a little bit. So you see the actuator location actually matters a lot of this training performance. So the next one is about a different observed state. So we have 4 sets of different observed states. We have the first one is in the flow field in the weak region, like weak area. We have a bunch of the props which provide velocity to the observed state, to the agent. So we also have the second one and the fourth one, which is also in the flow field and provide the velocity component. So we have this one lift on the airfoil surface. It will provide pressure props. So when we compare this, it has a different training. Basically, we show here is a moving average quantities about the lift coefficients. So we see the first cases, which is located in the weak area, have the hair training performance, where the second and the third is this one and this one, which has a relatively comparable performance. So the worst is this one, is this cases, which has a less props on the airfoil, and you see the training history is actually doesn't quickly converge. It takes a longer time to get a trend. So this is basically the primary results we get from the. So here comes the conclusion. So we have did all this bunch of the simulations and the tests, and after we do all this work, we come up with a preliminary summary and help us to work on more challenge flows, for example, high Reynolds number, turbulence flows. So as we see, we change a few bunch of parameters in the reinforcement learning control design, and we do see like a reward function doesn't really have a significant effect for the training section. However, we have the actuators, observed state, and actuator locations which do affect the control. So before we go, I want to mention because a reinforcement learning agent is based on a gradient descent problem. So for the optimal problem, you already have these problems. Is it going to find the optimal? Is it going to find the local minima or global minima? So those type of the problem is really depend on how you initialize your problem. For example, if you initialize your problem over here, so you quickly find the local minima, which turns out to be a global minima. If you located your problem here or here, you also quickly find the local minima, but those local minima may not be the global minima in the optimized problem. So that's why we think playing those parameters, for example, actuator types, observed state, and actuation locations can help us get idea about to address, at least give us idea about how the problem looks like. So that's all about today's talk. Before we go, I would like to acknowledge the computation resources provided from the SF Access project with a project number of PHY230144. And thank you very much.